So as I mentioned in my last video, there are certain inequalities where in the context of how we're talking about them, they really only make sense if we actually limit them on both ends. For example, if I was talking about how something happened over a period of time, it wouldn't really make sense for me to talk about negative numbers because negative time doesn't exist. Or if I was talking about how much something weighed, again, it doesn't make sense to talk about negative numbers. There's no such thing as negative weight. So that leads us to the idea in this section, which is all about compound inequalities. So our essential question in this section, what is a compound inequality and how do we solve them? So what we have been talking about in these other two sections involving inequalities so far are, we have been talking about what is called a simple inequality. A simple inequality is an inequality that only has one, literally one inequality, so one greater than, one less than, symbol, or equal to, in each problem. When we combine two simple inequalities into one expression or one inequality statement using the words and or the word or, the result is called a compound inequality. Which makes sense. A compound inequality is a more complicated looking regular inequality. So what I mean by that is we might see something such as y is greater than 2 or y is less than 0. The word or is separating those two things to make it a compound expression. So there are two kinds of compound expressions as mentioned. One of them is an and compound inequality and the other is an or compound inequality. So what we're going to do in this lesson is we're first going to focus on compound inequalities involving and. We're going to talk about what they look like graphically, how you can see them written as a problem. Then we're going to focus on or compound inequalities, and then we're going to tie this idea of a compound inequality back to where we actually have to do a little bit more work to solve. So a compound inequality involving and, if you think about what it means when we use the word and uses the idea of an overlapping region, meaning that both things must be true. You must be 18 years old or older and a citizen of the United States, registered to vote, in order to vote in an election. You must be, at least in the state of California, 16 years or older and hold a valid California driver's license in order to drive a car in the state of California legally. So, and uses this idea that both things must be true. This overlapping region in future classes you'll hear described as an intersection, meaning when both things are true. And we are looking for numbers that satisfy both inequalities, something that must be true in both. There are three main ways that you will see these written. You will see them written literally with the word and between them. X is greater than 0 and x is less than 5. I want you to think for a minute. Think of a number that is true for, a number that is greater than 0 and a number that is less than 5. So you're looking for a number that meets both of those requirements. So a number could be 2 or 3 or pi or 1.4, but it meets both of those requirements. It's both greater than 0 and it is less than 5. Another way you might see this is as written with two inequality symbols. So two less than symbols we can see right here. So this expression in number 2 would read, or this inequality in number 2, 0 is less than y is less than 5. Or if we wanted to translate that into English, that's a little easier to understand. Y is a number between 0 and 5. The last way we could see this written is using interval notation, and you might see it written sort of as x is in the interval from 0 to 5, but this ties back to an earlier lesson talking about interval notation. This is the interval from 0 to 5. Notice that there's parentheses, meaning that neither 0 nor 5 is included. So a number between 0 and 5, not including 0, not including 5. So let's rewrite these three inequality expressions or intervals. Let's rewrite them in the opposite form than they're in, and then let's go ahead and graph them and look at what we see when we do that. So let's actually start number 1 here by graphing. So I'm going to add some numbers to the bottom. It's important that you go by the same scale factor, and I'm just going to label every other number. Now remember, since this is a number line and there are arrows on the ends, that you don't have to start at 0. 0 doesn't have to be in the middle. You just have to make sure that we are covering the numbers that we need for this particular compound inequality, which in this case is 3 and 10. Those are our important numbers, our key values for plotting on a number line. So I'm going to look at the first thing that I see here. X is greater than 3. So greater than, not greater than or equal to, which means open circle at 3, pointing to the right. And then also x is less than or equal to 10. So closed circle, not at 12, but at 10 and pointing to the left. And I want you to think about what this is saying before we finish off what this graph looks like. We are looking for a number that is greater than 3 and less than or equal to 10. So I want you to identify in your head a number that meets both of those requirements, that falls within that range. So 5, 7, we could get fancy and say pi, 3.14159. Anyways, all of the numbers in between those two numbers fall within this inequality or make this inequality true. So if you look back at our graph, what we're basically saying is every number between 3, not including it, and 10, including 10, every number in between those two numbers and including 10 is a true statement for this inequality, and it sort of looks like a little line segment. Now, if we were going to rewrite this using interval notation, this open circle means that we would have parentheses, and what number is that open circle at? It's at 3. And the closed circle, which is at 10, means that we would have a square bracket here. So this is what this would look like written using interval notation. And if you need a refresher on interval notation, I recommend that you go back and watch the video on 2.1 that involves inequalities, interval notation, and graphing. So looking at number 2, the key numbers that we need on our graph, -2 and 0. I always like to make sure that I have at least 3 numbers on my number line. At -2, I'm going to have a closed circle. Since there's a line underneath this inequality, we are looking for all numbers that are -2 or more, but also that are less than, open circle, 0. So open circle at 0, so this teeny tiny little line segment here. All the numbers between -2 and 0, -1, -1/2, everything in between those two values. And if we rewrote this using interval notation, closed circle at -2 means square bracket, open circle at 0 means parentheses. This would be our interval notation. Now, number 3 is already written in interval notation. So let's first write it as an inequality. And if you want to, you can go ahead and pause the video and do that on your own. Otherwise, we can do that together. -5 and 2 are the two values. Choose your favorite variable. I'm going to choose x. The inequalities in between are both going to point this direction. And then this is a square bracket, so this should be an or equal to, and this one is parentheses, so I don't need a line underneath the other one. And go ahead and pause this video and graph this compound inequality, this and inequality. So here we have it, closed circle at -5, open circle at 2, and connecting with the line segment, stating that every number, -5, all the way up to 2, but not including it, is a solution to this and inequality. Now let's go ahead and look at the other kind of compound inequality, an or inequality. So compound inequalities involving or are very different than and, because before when we talked about an and compound inequality, both things must be true in order for us to be talking about that solution set or the numbers within that range. Now when we're saying or, we really mean that a number that is true in the first inequality or the second inequality, or possibly a number that is true in both, is a solution. So the combined regions that we're talking about here are called the union, and they show the numbers that are solutions of either inequality, either or both. Note that this means that both inequalities don't have to be true, but at least one of them has to be true. A real-world application of this, a great one and a scary one, is an elevator. An elevator typically has a limit to the number of people or a weight limit. Either of those two things going above what they should be could cause the elevator to not function correctly. We don't want to go over the maximum number of people, but we also don't want to go over the maximum weight. So this would be an example of an or inequality. There are certain other types of things where there is a weight or a height or an age requirement. Sitting in the front seat of a car, you either need to weigh a certain amount, thus making sure that the airbag will protect you and keep you safe, or you need to be a certain age or height, I believe it's height actually, a certain height at which the airbag will still safely protect you. So the idea of or meaning one thing or the other thing, but it's also possible, well, the last time I sat in a car, I met the age, height, and weight requirement for the airbag to keep me safe. So multiple things can be true at the same time, but at least one of them has to be true. The two ways mathematically that you might see this occur are either with the word or in between them, or using interval notation. And when we use interval notation, this U is the way that we combine, U for union. This allows us to combine two intervals together. So let's go ahead and look at some examples. Number 4 says x is less than or equal to 4 or x is greater than 7. Let's look at each of those as separate pieces and graph each one separately and then see what's happening on our graph. X is less than or equal to 4 means a closed circle at 4, pointing to the left, getting smaller. X is greater than 7 means an open circle at 7, pointing to the right, getting bigger. So looking at this graph, what's an example of a number that would make either of these inequalities true, or either would be in either part, either arrowed line, segment, ray, section of our graph? Well, 4, 3, 10, 100. What's an example of a number that wouldn't make this true? 5, 4.1, 6, 7. So being able to look at the graph and identify those two things. Let's go ahead and write this in interval notation now. So we're going to have two different intervals connected with a U. Looking at what's happening, x is less than 4. Less than means going down forever, so that's negative infinity. It's going up to what number? Well, it's going up to 4, and that's a filled in circle, so I use a square bracket. Unioned with 7, open circle means parentheses, up to infinity, which also means parentheses. Let's look at number 5. X is greater than 2, so open circle at 2, pointing to the right, or x is less than or equal to negative 1, closed circle at negative 1, pointing to the left. So here's my graph. If I wanted to write this as a compound inequality, negative infinity up to negative 1, union, positive 2 up to infinity. This should be a square bracket since it is a filled in circle. This should be parentheses since it is not. Let's rewrite number 6 as an inequality, and then I'm going to have you pause the video and try and graph it on your own. So negative infinity means we're going down forever. So x is less than, and the key number there is 5, and this is parentheses, so no line underneath. Or, and I need to physically write the word or so that it's clear that that's the type of compound inequality we're talking about. X, so we're starting at 10, greater than or equal to, since this is a square bracket. X is less than 5 or x is greater than or equal to 10. Go ahead and pause the video and try and graph this on your own. Okay, open circle at 5 pointing to the left, closed circle at 10 pointing to the right. All right, we're going to step away from graphing. We've gotten the idea of basically what a graph looks like for a compound inequality. An and graph points towards each other, and or graph typically points away from each other. We are going to talk about some special cases at the end of this video. Now we want to move into what happens if we actually have to do a little bit more math to get to the final answer. What if we have to apply the techniques that we learned when we were solving an inequality when it was a simple inequality to what we are already learning here? Okay, let's look at examples 7 through 10. What I want you to do first is I want you to look at all 4 of them, and I want you to identify which ones are and inequalities and which ones are or inequalities. So pause the video and do that. Okay, I'm hoping that you notice that the 2 that literally say the word or, those are our 2 or inequalities, which means the other 2, even though they don't say the word and, they are set up to be and compound inequalities because the variable is trapped in between the 2 values. Even though there's other things going on, that's still what's happening. The variable is stuck in between 2 values, meaning it has to be true for both. Both things have to be true. So when we're solving an and compound inequality, and we have to do a little bit more work than just graph it or translate it into interval notation, what we actually do is temporarily pretend that this is not here. If this wasn't here, what would you do to both sides to solve for x? You would add 2. And that would give you that x is less than 6. But I can't just cross things off because I don't like them. That's not how math works. What I want you to notice is that because there is a compound inequality, there are actually sort of 3 sides to the equation. Usually we just talk about 2 sides, but there's 3 sides. There's 1 here on the left, there's 2 here in the middle, and there's 3 on the right, which means if we go back to the addition property of equality, instead of just adding 2 on both sides, I now need to also add 2 to this third side in order to keep this inequality balanced. If I add -3 to 2, I get -1. I'm going to bring this inequality symbol down. So now we have that if we added 2 to all of the sides, we actually have the inequality -1 is less than or equal to x is less than 6. Or the interval square bracket -1, 6, comma. Let's actually jump down to number 9 since we said that number 9 is the other inequality that involves and, since there's no or. So again, I want you to think of this as if it's being divided into 3 pieces. So looking at the middle piece, what do I need to do to isolate 3x? Well, the first thing that I need to do is subtract 9. That would make these 2 things add to 0. So I need to subtract 9 here, and I need to subtract 9 here. -4 minus 9 is -13, is less than the 3x that was already in the middle, is less than or equal to 16 minus 9 is 7. Now, still having 3 sides, so I'm going to kind of redraw those little lines in. I want you to see that. In the middle is 3x. My ultimate goal is to isolate x, so what do I need to do? I need to get rid of 3. How do I undo multiplication? I divide. And I'm going to come up here. I'm out of space a little bit. 13 and 3 don't evenly divide, so we're just going to leave that as -13 over 3 is less than 3 divided by 3 is 1. So just x in the middle is less than or equal to 7 over 3. That doesn't simplify either. Remember, we always simplify our fractions, and if they don't simplify, we leave them as improper fractions. If I was going to write this using interval notation, -13 over 5, comma 7 over 3, square bracket here, parentheses here. Here's the beautiful thing about or inequalities. When we're solving an or inequality, it's already separated into 2 pieces. So you just need to solve each of the 2 pieces and then write your final answer. So if you look back at number 8, this is already solved. It cannot be simplified. It's already simplified. X is greater than 3. The one that we need to solve is this, -2x is greater than or equal to -4. And how do we solve that? Well, we need to get rid of this -2 that is being multiplied. So we divide. Don't forget, when you divide by a negative number with inequalities, you have to flip that inequality sign. That's going to give us x is less than or equal to -4 divided by -2 is +2. So the final answer here is x is greater than 3. That's right here. Or x is less than 2. Less than or equal to 2. If I was going to write that using interval notation, I'm actually going to write this one first. Less than or equal to -2 means -infinity up to 2, square bracket. 3 to infinity is x greater than 3. Go ahead and pause the video and try and work through number 10 on your own. Notice that this x is greater than 3 is already done, so you just need to solve the other one. All right, hopefully you've had time to solve this. We're going to subtract 3 from both sides. 2x is greater than or equal to 3. So x is greater than or equal to 3 over 2 if we divide both sides by 2. So this says x is greater than or equal to 3 or x is greater than 3. Now something weird is happening here. Both of these inequality symbols are greater than or equal to. Meaning if I was to graph these on a number line, here's 3 over 2, open circle, closed circle, pointing to the right. And then over here is 3, open circle, pointing to the right. There's some overlap happening here. And this is a special case in which it kind of is silly to keep two different inequalities. One of them covers everything. One of them covers both of them without having to restate them. So instead of having 3 over 2 up to infinity or 3 up to infinity, that's kind of silly. They're both going up to infinity. Which one covers more, or which one includes all of the numbers? It's this one. So the final answer on number 10 is just that x is greater than or equal to 3 over 2, or this interval notation version, 3 over 2 up to infinity. And that leads us to our very end of this video. Can special cases happen with inequalities in the same way that we talked about them happening with equations? And the answer is yes, we just saw one. So what we're going to do is we're going to look at 3 different cases, and we're going to try and figure out what's going on within each of those 3 cases. So what I'm going to do first is graph each of those 3 cases. So go ahead and pause the video and on a number line, graph what you're seeing. Okay, I'm going to label these. Let's call this A, B, and C. For A, this looks like an OR graph. X is greater than 3 and x is less than 2. So in order for and to be true, that means that both things need to be true. Is there a number that I could possibly plot on this number line that is true in both of these inequalities? Well, no, there's not. This looks like an OR graph, and it's saying it's an AND graph. Something can't be more than 3 and at the same time be less than 2. That means that this is really a no real solution situation. There isn't a number that satisfies both of these things, and something has to be true in both in order to use AND. Let's take a look at B. X is greater than 3 or x is less than 5. Not and, only one of those 2 things has to be true in order for it to satisfy this inequality. Well, look at what's happening. X is greater than 3 means every number from 3 up to infinity, or less than 5, every number from 5 down forever, which means that includes 3 now because 3 is less than 5, and it includes 5 because 5 is more than 3. This is actually covering the entire number line, which means this is all real numbers, which we could use interval notation. So what this is saying is that every number is true in this statement. Every number I plug in for x would be true either that it is more than 3 or less than 5. And then let's look at the last one, C. X is greater than 3 or x is greater than 5. So notice both of them have arrows pointing the exact same way, which makes it sort of silly to talk about 2 separate inequalities when one of them will do the trick. And which one will do the trick in this case? It looks like x is greater than 3. If x is greater than 3, then we also are including the entire inequality of x being greater than 5. So this could just be 3 to infinity. That covers all of the answers there. So these are some examples of special cases. I don't want you to focus too much on them, but be aware that you need to watch out for them. And then the importance of really visualizing what you're talking about on a number line is going to help you when those special cases arise. So let's recap what we did in this section. We defined that the type of inequalities that we've been working with up to this lesson were simple inequalities, one inequality in one problem. We built on that idea today by talking about compound inequalities where there is more than one inequality within a given problem. There are 2 types of compound inequalities. There's an AND compound inequality, and we talked about the different ways that you can see that written with the word AND, written as an inequality with a variable trapped in between 2 numbers, written using interval notation. And then an AND inequality typically looks like a line segment when we graph it. That an AND inequality means that both pieces must be true. It needs to be something and something else in order to meet the requirement there. And then lastly, we talked about OR inequalities where not both things needed to be true, but either or the other or both on some occasions can be true to be talking about an OR inequality. We talked about how we use the letter U for union to tie together 2 different intervals using interval notation. And we talked about how when we graph an OR graph, typically they're going to be arrows pointing in the opposite direction, but there are other special cases to consider as well. I look forward to supporting you on this more in class. Leave a comment below or let me know if I can help you out. Thanks for listening. X is less than 2.